Hey, it's Tony from Adafruit, and in this video I'm going to look at some experiments with color synthesis using NeoPixels and CircuitPython or MicroPython. So this will probably be a couple part video series, maybe 2 or 3 parts, because I really want to explore how do you animate colors and make really interesting effects, but not necessarily without having to dive into all of the intricacies of like really complex algorithms and code. We'll look through maybe some examples of that, but I hope at the end of this to have an interesting framework for generating animations that's a little bit easier than just sitting down and saying, okay, I'm going to write a pulsing, glowing animation, and step one, what do I start with? Step two, how do I move to the next step? I think by turning this more into a signal processing problem or like a synthesizing problem, then it might be a little bit easier and more fun to experiment. Basically, I want to be able to experiment and try different things. Have some knobs where I can tweak the animation, the speed, the color, the intensity, that type of thing, so that I'm not looking at the animation so much as what code do I need to write. It's more of how do I want to set these values, like the speed and the colors and things like that. So in this first video, this is going to be mostly some experimentation. It's actually, we're going to run through a bunch of experiments that I put together to help me kind of guide my way towards, I think, what the final thing is going to be, because I don't know exactly what the final end result of this will be. Like I said, I have some goals in mind for what I want to do. I want to make animations a little bit easier and have that higher level control of speed and color and things like that versus the really low level of, okay, use this math operation and now use this operation. And so just for a little bit of background too, a few weeks ago I was at the Emerald City Comic-Con and had something like this. This was my Iron Man arc reactor, so I had this on my chest like that. Under your shirt, it looks really cool, it glows. And this is, just animating some basic effects, and it's going to loop through random effects. It's going to go through different colors and things, but you can see it's just doing a simple pulse animation of the different colors on here. I can press buttons to flip through. This is a cycle animation on here, and then this has a heartbeat animation. But again, this is really just signals that are driving this animation. So this heartbeat animation is an exponential decay signal. So it flashes really brightly and then fades down exponentially over time. And so I'm literally just animating that over time, which made me think about, these animations really become signal processing problems. Like if I go to, let's see, this animation right here. So this is the chase animation. Let me pick a better color here. Let me cycle through a bunch of the colors. It has a ton of combinations, but there we go. So you can kind of see in chase animation, really all that this is doing is each of the pixels is having a sine wave that's computed based on the position, and the position of the pixel changes the phase of the sine wave. Now we'll come back later to what all of that means, but really this animation can just all be encapsulated by a sine wave or a signal. By just changing the parameters of that sine wave, it creates that cool kind of chasing effect. And so I'd like to get to a point where I can explore and try out these different animations, potentially without any code. I think it would be really neat to have like maybe a graphical editor, but we're probably not going to get there yet. But to make this experimentation possible with higher level code that's letting me change things like the frequencies or the types of signals that I want to generate, so that I'm not having to go in and actually change all of this line by line code. So I want to create some of these high level primitives, and I think in the next few videos or so we'll look at how I do that. So let's kind of dive in here and get started. And like I said, this is going to be MicroPython and CircuitPython specific. I'm doing this on a CircuitPython board, but this will work also on MicroPython. And the code, I've put comments in there that kind of explain there's some small differences in how you use the libraries that we'll look at here. So let's get started and look at the main view with everything. Let's jump here. So, okay, so the main view in the upper right hand corner right here. So I have, this is a Feather M0 Ada logger that's loaded with the latest version of CircuitPython. But like I said, you could use any board. You could use like an ESP8266 that's running MicroPython, anything that can drive NeoPixels, because as you see, I have a little ring of NeoPixels connected right here. And I'll go through the wiring in just a moment here, but it's pretty straightforward. You'll need to wire this to your board. So I have the ground connected to the ground of my board. It's through this little green wire that goes to my breadboard, because we'll come back to why I have a breadboard here later. We're going to add some extra components. This green wire is the signal, the data input line to the NeoPixel. That's connected to a digital I/O line. This is D6, digital number 6 on this M0 board. And then the red wire is the power line for the NeoPixels. Now the power does get kind of tricky with NeoPixels. If you're driving a lot of NeoPixels, they can pull a lot of current. Each pixel alone can pull 60 milliamps of current. You multiply that across 100 pixels, you're pulling 6 amps sometimes. I mean, that's maybe not 6 amps, but 600 milliamps. That's almost an amp of current for that many pixels. So that's a lot of current to pull. So you don't want to pull that from like a power regulator on your development board. Check out the NeoPixel Uber guide, which actually I will remind myself by opening it right here. Very, very good guide to check out. This has everything you would ever want to know about powering NeoPixels, like how to compute how much power they're going to pull, what kind of power supplies to use. So check out the Uber guide if you're not really sure how to power NeoPixels. But also one little note, if you're powering from a feather board or a board that uses 3.3 volt logic, then you do have to be careful because the voltage that you power the NeoPixels with has to be very close to the logic voltage that your data input line is driven by, that green wire right there. If they differ by too much, the NeoPixels won't see the data input signal. It's going to be too low of a voltage for them. The way I like to power these on a feather board is I plug in the power line for the NeoPixels. That's the red line right here. I have this plugged into the VBAT, or the BAT pin, B-A-T-T pin on the feather board. And what that does is that gives me the output of a LiPo battery, which I conveniently have plugged in right here. So I plugged in the battery to my feather. So that's giving me the raw battery voltage as power right there. So these batteries run at 3.7 volts, which is perfect because if the pixels are driven by 3.7 volts, then the I/O from the board is 3.3 volts. That's close enough. It's within the spec where the NeoPixels will be able to see that signal. The problem would be if I powered these pixels from 5 volts, but my I/O is 3.3 volts. In some cases, that difference is just a little too large and the pixels won't see it, your pixels won't light up, and things don't work. So if your pixels don't work, take a really close look at how to power the pixels. And there are a few little things that I mentioned, and when we look at the code, I mentioned some guides. So if you have to use a 5 volt power supply and 3.3 volt I/O logic, you can add a diode in series with your power. You need a beefy power diode because it's going to have all of the current going to the NeoPixels going through it. But that will drop down the voltage by like 1.2 volts or so. So that will basically reduce the voltage of your 5 volt power supply down to like 3.7 volts-ish. And that'll be good enough also to drive them. Or you could use a level converter to boost the level of your I/O that drives the NeoPixels from 3.3 volts up to 5 volts. That will help. If you happen to have a board that has 5 volt I/O, although I don't know of any MicroPython boards that have that natively. Maybe there's some variations of the ESP8266 that added level shifters or something, but I seriously doubt it. So that would work too. If you've got a 5 volt I/O board, then use 5 volts to power your pixels. But long story short, if you're using a feather like I am here, I like to use the BAT pin and then plug in a little 3.7 volt LiPo battery. Make sure it's charged up because it will pull some of the power from there. And then that just simplifies a lot of things so that no matter what, and there are some strands of pixels that don't like to be powered by 3.7 volts because that's technically a little bit below, I think, their spec. So even then, you still might be in trouble. But I've never run across a strand yet that hasn't worked off of this kind of setup like that. So, okay, so word of the wise, that's just some general gotchas with NeoPixels. But to come back to this idea of synthesis, so like I said, this video, I'm going to walk through 6 experiments that I did ahead of time. So I wrote a bunch of code, and we're going to walk through, it's a progression, so we'll look at a very simple example, and then we're just going to keep building on top of that to see how to go from raw animation code to higher level signal processing code that's a little bit easier to change. And my inspiration is modular synthesis. So I'll put a link when this goes up on YouTube. Look in the description below. You'll see links to all of the web pages that I'm looking at right now. But this is a page for modular synthesis, which, if you aren't familiar with, this is basically a way to synthesize music by combining signals. And so I recommend read this page or maybe do a YouTube search, look up like the Moog, M-O-O-G synthesizer. Was a really kind of well-known synthesizer that was really popular in the 70s. But these modular synthesizers all had the same concept of you generate a bunch of signals. So you have like a sine wave signal, or you have a square wave, or a pulse, like a triangle wave, different signals, and they can have different frequencies and different amplitudes. And you combine them in interesting ways to ultimately drive a speaker. So, if you take a sine wave and you modulate it at like 440 hertz, 440 times a second, and you drive it with a certain amplitude that it can output enough voltage to move a speaker coil, then that will produce sound. That'll produce a tone that you hear in your ear as like the letter A, like the middle C. I think it's letter A. I can't remember exactly, but that's, it's a tone that you will hear. It's a flat tone. And then you can change that sine wave. So if you change that frequency a little bit, that will change how you hear that tone. You can modulate the frequency so that maybe the frequency changes over time based on another signal. And the way these modular synthesizers would work is you would plug together all these different cables, basically like much larger versions of, little hookup wires. You would just hook up like, okay, I'm going to plug my sine wave in to maybe the frequency input of another component. And so you chain all these things together. You have this big rat's nest of wires. But ultimately, you were just combining signals together to drive that speaker or to make sound output, to drive a voltage. And I was thinking about colors and animations, and it's not that different. You can think of it as a signal problem, where a signal is just like a value that changes over time. And so if you think of a NeoPixel, it has three components that define its color. There's a red value, a green value, and a blue value. And those just happen to be bytes, which are just values between 0 and 255. But think of that as a signal, because that 0 to 255 value, if that changes over time, that's a signal. So, it might be stuck, at a value of 0 forever. So the pixels are turned off. But maybe something's driving it so that it's oscillating between, smoothly from 255 down to 0, back up to 255, back, down to 0. It's smooth oscillation like a sine wave like that. And if you view that over time, you would see it would look like a sine wave going across the screen. But when you see it, if you apply that to the NeoPixel, you would see it as color pulsing. So the color going from like fully on to fully off and back again. So I kind of thought of this idea, thought that it would be interesting to apply the ideas of synthesis and music synthesis to driving NeoPixels. And I can't take a lot of credit for this. This is not a new or novel idea, because I also was inspired by this thing called Scanimate. And Scanimate was taking that idea of modular synthesis that the music world kind of pioneered and applying it to video. And so this was a cool thing in the 70s and maybe even the 60s, where they basically took that modular synthesis idea and said, instead of driving a speaker coil with it, let's drive the tube of a television. So that, a TV is really just, there's like a scan, there's some magnets that drive an electron beam, and it scans across the screen very quickly, and the magnets are just modulated in a certain way so that there's like a vertical retrace and there's a horizontal retrace. And depending on how long it spends at a certain point in time, that's just more intense of a signal that you get there. So if you modulate those magnets, again, you can just think of this as a signal processing problem. Just what signal do you feed into those magnets to control how that electron beam scans across the television tube? And then that will just change how the tube lights up and what you display there. And so Scanimate was a neat video synthesizer that took that idea of, build up all these primitives of sine waves and square waves and triangle waves and filter them in different ways, and then apply them to the magnets on a CRT television so that you can produce these different effects. And then if you set up a camera that records the output of that CRT, you can record that and put that into like a movie or a film or something like that. And it was used in a lot of commercials and all kinds of things back in the day, apparently. And this has been replaced by modern computer graphics, where instead of driving coils on a CRT television, you just produce all of this in memory and render it out into some digital file that gets projected on, a digital projector in your movie screens and things these days. So we don't do things with the analog way, but those same principles I think can apply to things like driving NeoPixels, where again, I want to think of this as a signal processing problem. So I want to think of it, how do I change that red, green, blue color signal that goes to the NeoPixels? How do I change that over time? And then can I build up the knobs and the different like switches, the ways I can tweak and combine different signal processing primitives like sine waves and filters so that I can change the animation effects of that NeoPixel. So that now I'm not writing the code to say, okay, I want to pulse this NeoPixel, and so I need to think about how do I go from a low value smoothly to a high value. I just think of it as, oh, a sine wave looks like a pulse. If I feed a sine wave into the color, then the NeoPixel is going to pulse. And if I want to make it faster or slower, I can change the frequency of that sine wave. Imagine like a dial. You're just tweaking, changing, like increasing the frequency to make it faster, decrease it to make it slower. So that's what we're going to look at in this video. I'm going to go through some experiments. So let's dive into some of the code that I have here. Oh, and I hope that that was not too stuttery. I just noticed my CPU usage was a little high on that page because it was had some animations or things on there. Unfortunately, sometimes I'm right at the limit of being able to stream and also show videos and things. Anyways, though, when this goes up on YouTube, look in the description below and you'll see a link to this GitHub gist. This is the URL up here. This is the code that we're going to run through. And this is almost like if you've ever used IPython. This is like an IPython notebook, but I'm doing it kind of the manual way, where this is just a big source file. There's 6 experiments in here, and they're all commented out. And the way that this is going to work, we're going to walk through this and uncomment each experiment as we go and try it out. And then I'll walk through and talk about the code to see how it works and how it builds on it. So we're going to start with the first example. It's a real simple, basic example of just pulsing the color of the red pixel on and off using a sine wave, just directly with this code. And then I'm going to build on that to see, can I simplify this code so that instead of just the raw sine wave equation, I'm combining different signal elements together and transforming them in different ways for this. So that's what we're going to do here. So this is the code, and I'm just going to maybe minimize this. And so here's the code again, and I have it open in a text editor. And like I said, I have my CircuitPython board connected, but this will also work with MicroPython. But take a note in the guide here, I mentioned there are some small differences. Like right here, it calls out how you identify the pins on a board differ between different boards. So if you're using MicroPython, you might need to uncomment this line of code and tweak it a little bit. On the ESP8266, it uses pins that are identified by numbers. On other boards that are identified by strings. So you're gonna have to tweak this a little bit to make it work with your board, but I've tried to call out where all of those differences are so that you don't have to go hunt through all the files and things or all the code to figure it out. Anyways, though, this is set up just by default to work with the CircuitPython code that I have here, and it assumes that your NeoPixel is connected to board pin D6 like I have right here, but it's really easy to change that right here. And then you can adjust how many NeoPixels. This is a little loop of 12 NeoPixels that I have. Now the only animation I'm going to do is to light up all of the NeoPixels at once. So in a future video, I think we're going to look at how to animate pixels in different ways, the pixels within the strip. Right now I'm just thinking of this as, just animating all of the NeoPixels. But again, this will be a progression. We're going to build off of this stuff. So, okay, the very first thing I do in the code is just initialize the NeoPixel object. So I've shown this in a bunch of other videos. Basically, you create an instance of the NeoPixel object, you give it the pin, and then the number of NeoPixels, and then I just start out by turning all of the pixels off. So I fill them with a value of 0 and then write that out to the pixels. So that just makes sure that I start in a blank pixel state. And then if I just want to double check things, let's just make sure that I can turn all of the pixels on because I just want to make sure my wiring was not the best earlier. And so I noticed as I kind of moved some of the wires around, it wasn't working earlier. So I just want to double check this. So I'm going to have it turn all of the pixels red. And what I'm going to do, since I'm using a CircuitPython board that has that shows up as a USB drive on my computer, if I save this file, and this is a main.py file, I'm going to save this onto my board. And remember, everything else is commented out. So there's a bunch of code in here, but it's all commented, so it's not going to run. The only thing that's going to run is right up here. So I will save this to my board. So on my CircuitPython board, I'm going to save it as this main.py file. So we'll overwrite that. Yes, replace that file. And cool, so you can see all of my pixels just lit up red. And again, that's because with CircuitPython, when you write files to the file system, it resets the board so that you'll automatically see the output of your main.py again. Like it will rerun your main.py. So you can be in a quick little development cycle. So now if I want to reset these back to 0, I'll just set that to 0. If I want to turn off all the pixels, I'm just going to press the Control S key, or I think it's the Mac S key to save the file. So I just save the file back to the board again, and it just turned everything off because it ran. And I'm actually going to open up the serial REPL for my board right here. And by the way, if you're not using CircuitPython, if you're using MicroPython, you could use a tool like Ampy to send the file to the board. You could there are actually some little editors that are starting to come around. I saw there's an Atom editor, but it's for the microbit version. But look at some of the other MicroPython guides, which I'll put a link to in the description below to the category. And I have a whole guide on how to load files and run code using a tool like Ampy. Anyways, though, so I just opened the serial REPL for my board. And so again, because I'm using CircuitPython, it's in the mode right now. It's telling me that this auto reset is on. So as long as I save files and I don't do any input or touch anything on the serial terminal, it's just going to run my code and then show me any output here in the serial terminal. So this will be a kind of fast way to develop things. Okay, so let's look at the first example here, example 1. And I delineated all the examples just with like these big kind of block lines here, so you can scroll through the file and see each of the examples. So here is the code that I have. I'm going to uncomment this section of code. And so this is animating a red pulse just with a fixed equation for the code. So let's just save this and see what it does. So I just saved it, and you can see that all of the pixels are going from bright red to off to bright red again, but with a nice smooth pulsing animation. And so I'll explain how this works. Like, this is maybe the lowest level. So if you really just want to animate some pixels and pulsing, and you don't really care about making it easy to extend or change, this is the code to do it. And so I'm using a sine wave here. So I'm calling the math.sine function, and I'm passing in 2 times pi times this value 0.25, which is the frequency of this sine wave. So my frequency value is 1/4, or basically this means that this will happen once every 4 seconds. It will do a full sine wave oscillation. If I had a frequency value here of like 5, let's say, I can change this value, then this will actually change 5 times a second. So this is kind of where you can experiment with things. So if I save this file, then the animation is going to get a lot faster, and it's actually so fast that it's hard to see the updates. Like if I make this a value of maybe 2 times a second and save it, now you'll see, now it's a nice and fast animation. Whereas if I go back to the 0.25, it's going to slow down the speed of this animation. So you see it's, it takes 4 seconds now for it to do a complete on-off cycle of the sine wave. But this is cool. This is kind of the power of thinking of this pulse as a sine wave. When I want to change the speed of it, I don't have to think about like, how do I do this faster? How do I do this slower? I just think about change the frequency of the sine wave, change this single value, and I change the speed of this animation. And it's kind of cool that I can just experiment with other values. Like I can go with a smaller value to slow it down even more, like 0.1. And so now it's, it's going to take 10 seconds for it to do that full cycle animation here. Or I go, back to a higher value, like we can do maybe 2.5. So 2.5 times a second now. So it's going to be a lot faster animation here. So that's kind of cool. And that's again what I want to get at the end, is have a way to easily experiment with this. But you can see already the code for this is not easy to experiment with, because I've got this equation and it's kind of hard to understand like what all of these magic values mean inside of here. Like, why am I multiplying by 128 and then adding 128 right here? And so I'll show you some of the reasons for that. If you look at the equation for a sine wave, you can kind of think of it as, let's see, yeah, so here's kind of the general form of a sine wave. So you have an amplitude scale value at the front here, this a value, times the sine function, and then inside of there's 2 times pi times your frequency times your time value, which is your value that changes over time. Think of it as like your current seconds if you had like a clock you're looking at, plus some little phase value, which lets you change where the sine wave starts at a moment in time. So that's all that I have in this equation right here up to this point. So this 128 is the amplitude of my sine wave. Here's the sine function, 2 times pi times the frequency times my time variable plus 128. Oh, and let me put this page, let me minimize this because I notice it's cranking up my CPU usage when I have that open, unfortunately, so we'll minimize that again. But anyway, so, again, this is just that sine wave equation. It's just hard to understand because I've hard-coded in all of the values here. It's perfectly valid and fine to use this equation, and it's actually the fastest and most direct way to animate these pixels. But again, it's not easy to tell what's happening or to change or to experiment with this value. Now, the reason I'm multiplying it by 128 and adding 128 is that my color values for my NeoPixels expect a range from 0 to 255, and anything outside of that range won't work. If I have a value less than 0, the pixels don't know how to interpret that. It actually wouldn't even see that value. You would interpret it as it would wrap around to a high value because it's unsigned math. And then likewise, a value above 255, it's not possible to send that to the pixels because they actually take byte values that are sent to them. So it's kind of a problem here. Then my sine wave function in its general form outputs a value that goes from +1 down to -1. Whereas my NeoPixels expect if I want to turn them from off to on, I want to go from 0 to 255. And so that's what this amplitude and this offset value are doing. They're converting that range of -1 to +1 to a range that goes from 0 to 255. And so the way that works is if I have an amplitude of 128, that means my sine wave will now go from -128, or I guess -128 down here, all the way up to +128. So I'm going to oscillate between -128 and +128. But then if I add 128 to that, it's just going to push all those values up so that instead of going from -128 to +128, it's going to go from 0 because the lowest value of that sine wave is -128. But then I add 128 to it to offset it, so now I'm at 0. And so it's going to go from 0 all the way up to 255 because the maximum output of that sine wave part of this equation right here, the first half of this is 128. But then I add that 128 to it to offset it, so now it goes to 255. And so that's how I do that conversion between these two signals in effect. I mean, my NeoPixels expect a signal that falls within the range of 0 to 255. My sine wave function outputs a signal that goes from -1 to 1. So I'm just doing some math to offset it and scale it so that it falls within the range that my NeoPixels expect. And then I use the int function because the NeoPixels need an integer value. You can't send 25.72 as a color value. It has to be 25 or 26. It can't be in between those values. So the integer function will just convert a floating point value into an integer value because the output of your sine function will be floating point. It will give you nice high precision math. But in this case, NeoPixels don't know how to understand that level of precision. So I just throw out the fractional part of that and just convert it into an integer. And then the rest of this code, I just take this red color that I computed and I make a color tuple because the NeoPixel class expects colors to be a tuple of red, green, blue values. And so I'm setting my red color, and then the green color and the blue color I set to 0 for now because this is just a red pulse. If I wanted, I could make this a green pulse by just changing, now the naming doesn't match up, but just changing which value I set. So if I save that, now you can see I'm getting a green color here. So that's kind of cool. It's easy to change the color by just feeding this value into a different component for this. So I can go back to red if I want. And then I'm just filling all of the pixels with that color, writing them out, and then I'm actually printing out. So if I go back to my terminal, my serial output, you can see it's printing out. This is the RGB colors that are being set. And you can actually see the sine wave. If you watch this red value, see that it goes up to 255 at the top, and then it falls back down to 0, and then it goes back up to 255, and then back down to 0. So you can kind of see the sine wave values here. So it just goes up and goes down and goes up and goes down. So another way to visualize this. So you can even kind of see if you watch the color of the animation, when it goes up to a value of 255, it's bright red like right now, and now it falls down to a value of 0, and it becomes a turned off or a dark pixel at that point. So that's really how this first example works. It's just a sine wave, but I have to do some math to scale it and make it fit within the boundaries of the NeoPixel color range, so that 0 to 255 value. And again, this is a perfectly valid way to do this, but it's not easy to modify this because, like I've shown before, when I want to speed this up or slow it down, I have to go figure out where is my equation and, okay, what part of this equation is frequency? And then I probably have to go look up the sine wave equation and remember how to do that. So let's see if we can improve this a little bit. So let's go down to the next example. So example 2, now this is just a slight change, maybe not even worth pulling out as a separate example. all that I did in this example is I just made variables for each of these values that I hard-coded in here. So I just made an amplitude variable, a frequency, a phase, and an offset variable. And then I just changed my equation so that I'm just using those values. So you can see like 2 times math.pi times frequency times, now time.monotonic. Actually, this is a small difference between MicroPython and CircuitPython, which I'll have to edit the gist later to call this out. But basically, this is how you get the current number of seconds that have elapsed. And in MicroPython, you'll actually want to call the time.ticks_ms function and then divide that by 1,000 to get the number of seconds. But in CircuitPython, you can call time.monotonic, and we'll give you a monotonically increasing second counter. So this is a floating point value that gives you second accuracy. But again, anyways, I'm just showing that, you know, I'm doing the exact same sine wave equation here, but now I have some variables that are easier to tweak. So I'm not having to go search through my code and figure out, okay, where did I jam that frequency value in here? So if I save this and run it, it's gonna do exactly the same thing. So you see it's just doing that red pulse, but now it's a little bit easier. So if I wanna, you know, change the frequency, I can just adjust the value right here. Like say maybe, you know, there's 2, or maybe I wanna go back down to like 0.1 and slow it down, for example. And so you can see, yeah, it goes a lot slower like that. So again, just a very small tweak, but this is getting closer to that ideal of, you know, I want the knobs and the dials to change. Like imagine, you know, this is my modular synthesizer. And so here are 4 dials that I have to change this. You know, I can change the frequency, the phase, and the amplitude of this. Now the amplitude and the offset I probably don't want to change because those are very tightly coupled to the values that are driving those NeoPixels. So, you know, if I increase this amplitude to like 255, that's gonna create values that go way above the value that NeoPixels allow. Now, just for fun, let's see what happens when I do that. So you can see the animation's not working correctly. Like it's flashing up to these high values, and that's because the sine wave goes way above the value that it expects, and the way the NeoPixels see that, it just wraps around to a smaller value. So you get these weird discontinuities because the range I'm setting them is not correct. So, you know, this is nice that it gives me knobs and dials, but it's still a little confusing. And the other problem is like, okay, what if I want to do more than just drive my red color? What if I want to drive a blue color also? So, you know, I want like maybe my red and blue, maybe my red, or maybe my red and green color instead. So like, you know, let's say if I feed this red value to both my red and green components here, let's see what happens for this. So I save this. So you can see I get a yellow color now because red plus green equals yellow. So that's kind of cool in that it's a good way to you know, combine 2 different signals together. If I feed the exact same signal into the red and the green components, then I get a red and green, I get the combination of red and green colors. But maybe I want to invert this color. So, you know, basically I want to go from a red color to a green color. So I can take this red signal that's going to change, it's going to go up to 255, but when the red color is at 255, I want my green color to be 0. And then when my red color is down at 0, I want my green color to be all the way up at 255. So if I just invert that red signal, so if I take 255 minus that red signal and feed it into that green value, now when my red value is 255, I'll have a full 255 red intensity, but then I'll have 255 minus 255, that equals 0, so I'll have a 0 green intensity. And then at the opposite extreme, when I'm at a red value of 0, I'll have 0 red, so that's my red pixel is turned off, but then 255 minus 0, that means my green pixel is turned fully on. So let's see what happens when I save this. So this is kind of cool. So notice how it's now pulsing between 2 different colors. Instead of just red to black, I'm going red to green. And that's because I'm basically taking this sine wave signal and just using it to modulate the colors. So I'm basically driving my red pixel with it and then driving the green pixel with the inverse of it, or, you know, basically flipping it around so that when it's a high value, it's actually taking the opposite of it, taking the low value there, so that now I'm just turning on the green and the red pixel and just swapping in between them. But the nice thing is you actually see as it goes in between there that yellow state where your red pixel is half on and your green pixel is half on. So you get kind of like a mid-yellow color at that point. So it's kind of cool, but it's neat in that I don't see any of that in my code. Like, I'm not computing, okay, what's my halfway point, and make sure to turn the red pixel halfway on and the green pixel halfway on so that I get that yellow color. It just happens naturally by combining those signals together. It's just looking at that same sine wave and just applying it to two different components. And then I'm effectively changing the phase of this sine wave, if you think about it in some ways. So I'll show you in the next example a different way to change that green color so that it's out of phase. But I'm really thinking of it so that the phase is the value of where the sine wave is at a certain point in time. So that if the phase is 0, at time 0 your sine wave starts with a value of 0, and then at time I believe pi, because your phase is a value in radians, and in 360 degrees there are 2 pi radians. So halfway in between, or actually a quarter of the way, so pi over 4, you're going to be at the top of your sine wave. And so that means at a phase of pi over 4, you're going to get the maximum value. So if I change this phase value, it changes where the sine wave starts. So we'll come back to this in a second, but I'll show you how if I let myself tweak that phase, I can think of it as actually a separate red and green signal that are just out of phase with each other, so that I can get a neat effect like this. So we'll see more of that in a second. But again, so with this, oh wow, my cat, you might have heard her. She's, I guess she has a lot to say about signal generation and NeoPixel color synthesis. Anyways, so, like I said, with this second example, I broke things out into variables, makes it easier to change how it behaves, but it's not easier to add new signals because, again, I have to copy all of this math. And then if I'm breaking things out in variables, I'm going to need to copy all these variables because I probably want separate knobs I can tweak for each of those sine waves. If I want to feed a sine wave into red and another sine wave into green and have them, that have different frequencies and different phases and things like that, I need to duplicate all of these variables, and that's going to add up. It's going to take a bunch of memory. It's going to take a bunch of code. It's going to be kind of ugly, and then I need to go and search through my code and figure out, okay, when I want to change the green, what did I call the green frequency and things like that. So it's going to be messy. It's going to get kind of complicated very quickly. So let's see a different way to do this. So this is the third example that we'll look at, and I called this refactoring into a functional style. And this is starting to get a little more advanced, but I'll try to walk through kind of what I'm doing here. But what I tried to encapsulate in this example is the idea of taking a wave, a sine wave, and making it an object, an effect, or a function, so that I have this function that I defined here, this sine wave function, and this actually returns a function. So it returns a lambda function in Python. Lambda is a way that you can create a function. And so, because when you think of it, the sine wave is a function with a variable in time. So I need to pass a value into my sine wave to get an output value. And it's that time value that I feed into it. It's that time.monotonic right here that I'm feeding into it. And then it's outputting a value that goes between 0 and 1 based on, as time increases, that value, output value, changes based on a sine wave. So I can create a function that creates a sine wave function. And in Python, it's actually really easy to do that. That's effectively what I've done here. I made a function, this sine wave function, that will make a function. It returns this lambda function. But I can tweak how it generates that function. So I let you pass in an amplitude, a frequency, a phase, and an offset. So I can pass these into my sine wave generation function, and then it's going to just make a function and return that function. And that function is exactly the same sine wave function we saw before. So I just take the amplitude times the sine function times, and then into the sine function I pass 2 times pi times your frequency, times this t value. Now this is where the lambda function is necessary because, again, the sine function is a function that requires a variable to be passed into it. And so that's what this lambda function means, is I'm creating a function that takes one variable called t, and then inside of that function I can do this computation using the value of that variable t. And then I can add the phase to it, so this just does the proper sine wave computation and then add the offset value to it. End result is every time I call this sine wave function, like right here, I pass in the amplitude, the frequency, the phase, and the offset, and it will return back a function, so that now this red wave object is a function, and I can call it like a function. And you can actually see I call it right here like a function. So red wave, here's a parenthesis, and I'm passing in a value. And so that's just passing in to this t value, the current value. And the current value I just saved ahead of time. So I grabbed the current time value, but I guess I'll show you in MicroPython time, you would want to do the microtime.ticks_ms divided by 1,000. That'll give you their current time in seconds. It's compatible here. But so I'm taking that current time and I'm passing it into my red wave function, so that now I've kind of encapsulated the idea of a sine wave into a function, because that's what a sine wave function is. It's a function that takes in the value of some time variable and outputs another value. And then just as a helper, I made a function here that generates these sine wave functions. I could have written two separate functions. I could have written a red color wave and a green color wave function that encoded in the different frequencies and phases and offsets. But this kind of simplifies my code because I just encapsulated that idea of generating a sine wave function into a function I can call right here. There's two levels of functions happening here. It's like a function inception to wrap your mind around. But this is kind of cool that I can tweak these values here so that, notice in this example, I'm actually doing something a little bit different. So, I've got the same amplitude, a value of 128 for my red and my green wave. I have the same frequency, a value of 0.25 for both these waves, but I am changing the phase by slightly different values. So for my red wave, I give it a phase value of 0, and for my green wave, I give it a phase value of math.pi. And this just means my phase value is halfway, because a full cycle is a phase value of 2 times pi. That's how many radians are in a circle. But if I take half of that, math.pi, then that's basically telling my green wave, okay, instead of starting at the very first starting point where all sine waves start halfway into the sine wave. So that think of it like, the red wave starts with a phase of 0. So when the sine wave is at 0, the red value is at 0. But the green wave has a phase that's halfway into the sine wave, so that when the red is at 0, the green is actually halfway into it, which is at like the full value. And so that's how it oscillates. And actually, if I save this, it's going to run this code now. And so you can see it's doing the exact same thing. It's oscillating from green to red and back to green again. And that's because I'm now thinking of it as a red signal and a green signal that are completely separate. And you can actually see in the code right here, here's where I get the red value and the green value. And then here's where I compute that color tuple. And the rest of this code is exactly the same as before. But now, I'm thinking of it as red and green as separate signals that just differ based on the phase. And if I wanted, let's set this phase to 0 so that these are both exactly the same signal. If I do that, now I just have the yellow pixel fading again. And that's because my red and green pixel are fading at the exact same rate. Whereas if I go back and if I change that phase to math.pi, it's going to have them be exactly out of phase so that when the red pixel is on, the green pixel is off, and then vice versa. And I forgot, this is actually printing in the output, the serial REPL. It's showing for every moment in time the red, green, blue values. And if you watch this long enough, you can see exactly that happening. When the red pixel is really high, like right there, the green pixel goes down to 0. And when the green pixel is really high, the red pixel is back down at 0. And that's because there are two sine waves that are out of phase here. But I don't have to use values like math.pi. I could say, how about math.pi over 2? So I take a smaller phase value. Let's see how this changes things. So now my green color is going to change. It's at a slightly different offset. And so you can see how it's giving a slightly different effect. Like there's an orange kind of period. It's maybe a little bit longer than before. And if I look at the values here, it's no longer the case that when my red value is full 255, my green value is all the way down to 0. It's offset by a little bit there. And the cool thing is too, so I know, let's go back and set this to math.pi. I can change the frequencies to different values now too for these. So, my red wave, let's keep this at a slow 0.25 frequency. Let's change my green wave so it's a fast frequency of, twice a second. So, before I run this, think of it in your head. My red color is going to change at that slow rate, once every 4 seconds. But now my green color is going to be changing at a much faster rate. So let's see what happens when I do that. So this is going to do some interesting effects. So you can kind of see it's a little hard to tell, but it's going between like these red and green and sometimes some orange values here. And I know, let's slow this down. Let's, instead of 2, let's do like a 1 value, 1.0, and see if this kind of changes things. So yeah, now there's a little bit more of smoothness, but you can kind of see it's almost looks kind of random. It's doing, but it's still organic. It's not random in the sense of like, just randomly shooting between values. There's a smoothness to it, an organic kind of feeling, but it doesn't have a rhyme or a reason. I'm looking at it and it's hard for me to tell intuitively like what the next color is going to be. I see it going from like red, orange to yellow to green to back to red sometimes. It's a little bit interesting. And if I look at the colors here, you can actually see my red value is changing very slowly still, but notice that my green value is going up and down and up and down and up and down at different rates here. So it's changing at a faster rate, so that my green value goes up and down and up and down, whereas my red value in that same period of time is just going slowly up and down across there. So it's kind of cool, and this is really neat. This is getting closer to that ability where I'm just thinking of the color components as different signals, and I can tweak the knobs on these signals. I'm imagining my modular synthesizer in front of me, and I have my red sine wave, my green sine wave outputs, and I'm just tweaking the knobs on there to say, okay, let's set the frequencies to be exactly the same again, so that now they're exactly, out of phase and doing this nice, neat little pulse. But, let's speed up, or maybe let's slow down this red pulse even more. So now let's see what happens when I do that. And so it's, again, just tweak that little knob so that now, there's less effects, or, the red color comes on slower. And so you can see it goes through like that neat little yellow phase right there. And if I watch this over time, that yellow phase is going to become shorter, and then it's going to become longer, and it's going to change in really neat kind of organic ways. And this would be kind of cool, if you're just trying to make some kind of a neat organic animation, this would be one way to do it. And again, like, if I wanted, I could make a blue signal. So let's say a blue wave, and I just can construct another sine wave for this. I have to be sure to set that amplitude value to the right value, because again, remember, the blue signal goes from 0 to 255 like all the other ones, but let's give this a frequency of 0.75. We'll make this a fast signal, maybe no phase, and then 128 offset to get it back into that 255 value. And then in here, I can add a blue value, and this is going to be my blue wave function based on the current time. So if I do that, oops, I put an extra parenthesis in there. Let's pull that out. So there we go. And then I want to set my blue value in here. So now I don't know what's going to happen. Let's see. It's going to make some cool colors and things. So that's kind of neat. So you can see like the red, green, and blue values in here. I'll open up the terminal so you can see like here's my blue value now. It's got a sine wave that's applying values to it. My green value has a sine wave that's changing at a different frequency. My red sine wave is changing at an even different frequency. So this is pretty cool, and this is a really neat way to start thinking about animating these pixels. That again, if I wanted to code this animation up without using sine waves and signals like this, it would be really difficult, because I'd have to think about like, for each period in time, how do I organically transition my colors so that it looks really cool? And again, it's just so complex. I don't even know how I would do this without sine waves, to be honest. Like, I'd probably think of it as like manually setting frames of animation and just setting for each point in time, here's what color I want to have, and then keeping an array of those and just looping through that array of colors, which is perfectly valid, but that's really complex. If I just want this cool pulsing organic animation, a few sine waves are all I need to do that. So that's kind of cool, and that's again the power of refactoring into this functional style, where I have a function that generates sine wave functions. And so now I can really represent my color waves as sine waves, and I just create those sine wave functions, and then in my main loop here, I'm just getting the current time and then feeding that value into all of my sine wave functions for my red, green, blue color components, and then lighting all the pixels with that. So that's what's happening there. So let's comment that out, and let's move on to the next example. So So this example starts to get a little more complex. This is a big one, and this is, let's see, let's uncomment this example here. So I'll save this and we'll see what this does. This is just going back to that red-green pulsing animation. So you can see it goes from red to green and back again. But I've done some different things now. Basically, I tried to get rid of having to make my sine wave aware of the fact that it needs to generate values that fall within the color ranges. Because, you know, the pure sine wave function just generates an oscillating value that goes from 1 to -1, whereas my colors for my NeoPixels expect signals that go from 0 to 255. So that's a mismatch. You know, I can't just directly feed my sine wave into my NeoPixel color value because it's not going to generate colors that are large enough, or the values that are large enough. It's going to generate negative values, which mean nothing to the NeoPixel. So like I showed before, sure, you can apply an amplitude and an offset to the sine wave, but I don't like that because that complicates the sine wave. You know, we saw up above, I have to know, like, okay, what are these magic amplitude and offset values to work with these NeoPixels? And then what happens when I have a new strand of, you know, fancy NeoPixels that go from 0 to 512 or something like that? You know, they have more color precision. And suddenly it's like, man, I got to go through all my code and figure out where I hard-coded in all these assumptions that my signals need to be transformed into the 0 to 255 space. And so it's really hard when I'm just looking at those equations and those raw values for me to figure that out. So I thought a little bit about, can I encapsulate the idea of a signal that represents some value that falls within a range? Like the sine wave falls within a range of -1 to +1 values. No matter what I feed into that sine wave, as long as I don't change that amplitude value, it will never give me a value that's greater than 1 or less than -1. That's just the way the sine function works. So, you know, based on that, I can take that assumption. You know, if I represent a signal as an abstract thing that has a value I can get, and I know the bounds of that value. So I know that for this signal, it never goes above a certain value and it never goes below a certain value. It always falls within that range somewhere. Then I can transform that value to be within another range. And that I can just use a formula. It's called linear interpolation. I've done this a million times, and this is actually the formula for it right here. But if I have a value that falls within one range, I can transform it to fall within another range given the bounds of that range. So what I need to know is the current value of my signal and what's the minimum and the maximum values of that signal. And then I also need to know what's the minimum and maximum value of my target range, or my target signal. And then given those 4 or 5 values, I can get a new value that is my target value that's proportional to my signal. So if my signal is really high and like at its maximum value, then my target value will be really high and at its maximum value. But if my input signal goes really low, then my target value, my transformed value, will also be really low and all the way down to its lowest level. So I think of this as, can I automate that conversion from my sine wave signal that goes from -1 to +1 into a value that goes from 0 to 255 that's good for driving NeoPixels? And that's what I've done here. And so I've made this a little more object-oriented. So I made an abstract signal class right here. So I made the concept of a signal, and a signal is just something I can call to get the value of. So, you know, previously my signal was this lambda function. So I can call the function that my sine wave function returns, and I pass it my current time value, and it gives me back my sine wave value. Whereas now I have a signal class, and it implements this __ call function. This is a magic method in Python that basically means if I have an instance of this class and I call it like a function, it's going to call this line of code right here. Now in my signal class, I actually throw an exception because my expectation is I need to implement a class that inherits from signal. So I need to implement a sine wave signal, and it needs to fill in how to compute the sine wave, because the sine wave is just the start. Like, there are millions and thousands and unlimited number of other signals that I might want to generate. So, you know, I'm not going to always have one signal, but there's one concept of a signal, the base class for this signal. And so it just so happens that, it has no idea what a default implementation of a signal value is. It just knows that the things that implement signal need to be able to generate values using this call function. So that's what's happening here. And then what I do know is going to be consistent across all of my signals, or at least most of them, is that they have a range. So they have a minimum and a maximum value. And that's what is encapsulated right here, so that when I create a signal, I tell it, hey, here is your range of minimum and maximum values. And I store it as a tuple, which is just a set of two values, a minimum and a maximum value. And so with that knowledge, though, I can add some functions onto my signal so that if I have an instance of a signal, it will always have this transform function and this discrete transform function. And this gives me this nice place to put this logic of, given a signal that has an upper bound and a lower bound, I can transform it into another signal that has a different upper and lower bound. And I'll transform the value of that signal proportionally so that, when my input signal is at a really high value, my transform value will also be at a really high value. But it might be, when my sine wave is at a value of 1, now it's transformed to a value of 255 that I can feed into my NeoPixels. And similarly, when my sine wave goes down to a value of -1, I can make it so it transforms that value down to a value of 0, instead of -1. And it's cool in that now I don't have to pass these magic values into my sine wave function. When I want to change the frequency of the sine wave, I just tweak the frequency. I don't need to know, okay, I better go change the amplitude, to get it into the right space for this NeoPixel. I'll let the thing that uses the NeoPixel know that, hey, you've got a signal. You don't have to know or care what this signal is, whether it's a sine wave or a square wave or a triangle wave or whatever. Just know that I'm giving you a signal and you can transform this signal into whatever range you want using this transform function. And the math for this is just using something called linear interpolation. And I'll actually show in Wikipedia, I've shown this a bunch of times, but the linear interpolation is just a way to translate a function from one range to another range proportionally. And so this is the equation for it right here, and this is exactly what I've implemented right here, so in this little highlighted section of code. So again, the way this transform function works is it will get the current value of the signal, because remember, it's using this call function right here. That's what this little bit of the function is doing. Gets the current value of your signal, that's your x value. I know my x bounds, so my x0 and x1 from the linear interpolation function, so it needs to know an x0 and an x1 value. And so that x1 is your maximum signal value, x0 is your minimum signal value. I know those because I've told the signal ahead of time. I've stored that on the signal class in this self.range tuple. So the first component in the tuple is my minimum, the second component is my maximum value. And then I just ask in the transform function, you need to tell me what is the desired range, what is your y0 and your y1, or what is your minimum and what is your maximum value. And then I will transform my signal value into the range that you're asking for, so that now my signal doesn't need to know what range it needs to be transformed into. Whatever uses my signal can choose how it transforms that signal, so that I'm moving that logic of transforming my signal into a different domain or into a different set of values, so that it's not in the signal itself anymore. The signal is this pure sine wave, and whatever uses that signal can choose what domain it wants those values to fall into by just changing how it transforms it. Now you might notice this discrete transform. I just added this as a wrapper. All that it does is it calls the transform function, but it converts it to an integer. So it converts it to a discrete value, an integer value, which is handy because that's what my NeoPixels expect. So that's kind of cool. So that's my abstract idea of a signal. And then I implemented a sine wave signal, which inherits from that abstract signal, but now it's a little bit more pure and simple. It still has the same concepts. I added what's my amplitude, it needs to know the time and the frequency, and it just saves those as member variables. You can see right here, though, it calls super init. This is basically how you tell Python when you have a base class, you need to call its constructor explicitly, and that's what this super.init line does. And then I'm passing in this tuple value, so I'm telling my base signal, here is your range of maximum values. And so for a sine wave, your range goes from negative amplitude to positive amplitude. So I'm telling it, here's the values that you can expect. And so that way, whatever calls the transform function, because remember, since sine wave inherits from signal, even though it's not shown right here, it will automatically get that transform and discrete transform function added to it. And then that transform and discrete transform function, they'll know about the range of my sine wave because I told it, here's my amplitude that I set for that range ahead of time. Oh, let me just minimize this so I don't get as much CPU hit. But anyways, so I have my sine wave function. So now let's see what my main loop code looks like here. So you can see I'm creating a red wave and a green wave again, but now it's a sine wave object. And I love how clean this is. Look at this. It's just the same frequency and just a slightly different phase. Those are the only knobs. I don't have this concept of like, well, I need this 128 amplitude value and then I got to offset it by another 128 or whatever. Like, what does that mean? Just me looking at that code, I don't know what that means. But I can look at a sine wave and know, okay, this is a sine wave that changes once every 4 seconds because the frequency is 0.25. If I want to change this, if I want to change this twice a second, I can change this to 2.0. If I save this, and so now my red sine wave changes a lot faster. So this is really cool. I'm just simplifying my values, and that my sine wave doesn't have to know or care about how it converts itself into the NeoPixel format. Now where it does that conversion though, you can see in the main loop. So I'm getting my current time, and then now for this example, I need to still tell my sine wave what is the current time. And I'll show you in the next example, we're gonna make this even simpler, but for now it's just a time property that I have to set, or an attribute rather, on this class. So I need to explicitly tell my sine waves, here is your current time value. So I say redwave.time equals my current time, greenwave.time equals my current time. That's what's happening here. But then once I've set that time, then I can get my red values by asking my red wave signal, hey, do a discrete transform into the range 0 to 255. So this is going to call this discrete transform, which calls this transform function. And this is the magic step that says, okay, I've got this generic sine wave object, and it knows that it goes from a range of 1 to -1, but I want a value that goes from a range of 0 to 255. And that's where it's going to apply this linear interpolation on my sine wave function and make it fit within that range. And so that's really cool and pretty powerful, I think, because I'm just modeling my color waves as just pure sine waves. And then when I actually apply these to the NeoPixels, that's where I do all the logic and all the goo and all the knowledge of, okay, what is the range that my NeoPixels expect? So this is kind of cool because this is getting me closer to that ideal of just picking arbitrary signals and tweaking their values and combining them in different ways and feeding them into the pixels and letting the pixels figure out, okay, you've got a sine wave and you know the limits that it goes between, so that when it's at its maximum limit, light up to your maximum value, and when you fall down to your lowest value, turn off completely. So that's exactly what's happening here in this code. So by abstracting these things away and having this concept of an abstract signal and then building a sine wave on top of that, I can make the code a lot cleaner and a little bit closer. And again, if I wanted to add a blue sine wave, it's a lot easier now. I just create a blue sine wave. I can give it whatever frequency I want. We'll say maybe 2.0. And I'd want to duplicate the code and make it kind of similar below here. But you can see it's very clean and simple to create new sine waves in this example. So okay, so let's move on. There are 2 more examples, and I'll see if I can kind of speed through these. The last example might be kind of mind-blowing. It does some fun stuff, so I'll try to save some time for this. So okay, so the one thing that was kind of ugly about the example above is how I had to set the time. The time, if I go back up, and I'm just, we'll run this code in a second, you saw how the time variable, I have to go and manually tell my sine wave, here is your current time value. When in reality, it would be nice if I could actually tell my sine wave, you have a fixed amplitude, you have a fixed frequency, but your time value is actually another signal. Like, wouldn't it be cool if I can compose my sine wave out of other signals so that my time value is itself a signal, which could just be like the current number of seconds. That's a perfectly valid signal. There's no range to that signal. Like there's no maximum second count, at least until the end of the universe. There's no maximum value for that. So it doesn't maybe have a value that I could transform between different ranges. But I don't necessarily really care about that at all points in time. I just need the idea of a signal is some value that changes over time, and time itself is a valid signal. At a point in time, my current number of seconds is going to be different than 1 second previous to that. So that's a value that can modulate. And if I take that to its complete extreme, why don't I let all of the values in the sine wave be signals that I can change? So not just the time, but why can't I change the amplitude over time? Why can't I change the frequency over time? Why can't I change the phase over time? All of those different values. So that's what I'm showing in this fifth example. I've changed it now so that I still have a sine wave class right here, but maybe we'll dig more into this and how this works. I'm still passing it in fixed values for some things, but I can actually set these to not just fixed values. I can set these to signals so that when I compute this sine wave, instead of just always having a fixed frequency value that I set ahead of time, I could pass another sine wave in as a frequency so that my frequency for this sine wave is based on the frequency of another sine wave. And that's coming back to that modular synthesizer idea of, you take one sine wave and you use it to modulate another sine wave, and then you get these really crazy organic effects, because if you're modulating your frequency over time, that means you get a really fast moment in time, and then maybe your signal slows down, and then it gets really fast again, and then it slows down. So you can see some really interesting effects by giving the ability to tweak the inputs to one signal based on the outputs of another signal. And so there are two different things that I'm using this for. Well, really only one thing, I think, in this example, if I remember. The time value, I can make this a signal now so that I can feed in the signal, which is basically my clock, and it will just modulate the sine value over time, and I don't need to remember to set that. So let's kind of walk backwards and see how I did this. We'll start with the sine wave class again, so that it's similar to the previous sine wave class. It still inherits from signal. But now I'm creating these signal source objects instead of just storing static values. And you'll notice that my code has changed a little bit also. In the call function here, when I compute my sine wave, I'm still using all these attributes, but I'm calling them as a function. So I'm adding these parentheses here because, again, these things are now signals. Even if they're a fixed value, they're still a signal, because that's just a signal that never changes. It's a value of 1 forever, but I can still ask, what is your current value right now? 1. What is your current value in a second? It's still 1. But I've changed my logic now so that everything is a signal. And so I have to basically say, every time I compute this sine wave, go ask the amplitude signal, what is your current value? Go ask the frequency signal, what is your current value? Call the frequency signal function. Same thing for time. I can ask the time signal, what is your current value? Give that to me. Same thing for phase. I can tweak that over time. Now, one thing I do need to change is I need to change the range on this, because if my amplitude changes over time, my range will change over time. And so I added a property here so that this will override in Python, in the signal class up above. I switched it over now so that it has the range is a property instead of just a fixed tuple. And by default, it just assumes there's no value set, so it just returns a value of none. But subclasses like sine wave that know they have a fixed range, and that fixed range might change over time, can compute that value now. And so that's what I'm doing. I'm basically saying, okay, whenever something asks for my range, go ask what's my current amplitude, and then generate a range that goes between that negative and positive value for this. So, but this might be overkill. Like, you might not need a sine wave that modulates its amplitude all of the time. Like, it's perfectly valid to still keep that fixed amplitude logic. It simplifies things a lot. So I mentioned that in the comments here. But anyway, so the big change here is now, I have these signal source objects. Well, what do these things do? So that's what this class is right here. And I made this as a wrapper to simplify, because I want to easily be able to pass either a signal or a fixed value to any of these components. So my amplitude might be a fixed value, or it might be a value that changes over time. And it's kind of hard to encapsulate that logic because I need to know, like, if it's a fixed value, I have to go and read it. Whereas if it's a value that changes over time, it's a function I need to call. And I don't want to have all these if statements in my sine wave generation to say, like, if it's a fixed value, use it. Otherwise, call the function to get the fixed value and then use that. That gets kind of ugly pretty fast, and there's extra overhead for that I don't want. So I encapsulate the idea of, for all of these signals that depend on other signals, I create that signal dependency as a signal source object. So this is basically saying that my sine wave is built out of 4 other signals, and I could plug things into those signals. I could plug another signal into that, and it, my sine wave just knows that, hey, I've got 4 kind of slots, think of them, where I can plug in 4 different signals, and based on the values of that signal, then I know how to generate my sine wave. And then this signal source class gives me this set source function where that's where I can plug in a new signal value. And I just made it a little bit simpler so that in its initializer, I can pass in a signal source directly, and it's just going to automatically call this set source function. But we can look and see what this set source does. This is where I do this logic of, if you give me something that's callable, if you give me a function, then I will remember that function, and that becomes the source of this signal. So if I plug a sine wave function into this signal source, it will see that it's callable. This callable function returns true if something is like a function, like it can be called, which my signals are. Remember, I added that callable to it, where you have to implement this callable. So if I pass a signal in, then it's going to notice that it's callable, but I don't have to pass a signal in. I could pass just a regular function in if I wanted. So this is nice and flexible. But if it's callable, then I will remember that. So I keep track of what is my callable thing. And whenever something calls this signal source, so you might think of it as the signal source itself is kind of like a signal. I can call it. It's just going to call the signal that it remembered ahead of time, that self.source function or callable. It's going to call it and return its value back. And so that's what's happening right here when I'm calling this self.amplitude. It's calling the callable on my signal source, because remember, self.amplitude is a signal source right here. So it's going to call this callable, which is going to call whatever source signal callable it had and get its value and then return it back. Now, where it gets kind of fun is I might not call set source with a callable object. I might call it with a fixed object, like a value of 1.0 right here, or a value of 1.0 for this frequency. And in that case, this callable check is going to be false. And so that's where I fall through to this next case where I say, okay, if you don't pass me a callable, I'm going to assume that you've passed me some static value. And I will make a callable. I will make a lambda function that captures that static value. That's what's happening right here, is it's going to remember that source value that was passed in. And it's not obvious, but in Python, this actually works. It's going to remember this value so that now my source function, instead of being some function that you passed in and told me, I realized, oh, you didn't give me a function, you gave me a static value, but I'll create a function that remembers that static value and I'll set my source to that. And that's exactly what I do here, so that now later on, when my sine wave calls self.amplitude, it doesn't know or care whether amplitude was set with a static value or a changing over time signal value that's callable. It just knows that it's callable, and it's going to call it. And because it was set with a static value ahead of time that created this function that just returns that fixed value, it's just going to work. Like, my code just has to know whenever I want the amplitude, call it like a function, and you'll get the amplitude value back. So that's what's happening there. And actually here, I'll save this. I don't think I've saved it yet. So you can see this code is just, again, going the red to green pulse that I had before. But so that's kind of cool, and that's why I wanted to create that signal source. And then I figured, well, the time itself is a signal, so I made this frame clock thing, which is a signal. The clock is a signal, and I gave it the idea of, I call it a frame clock because I want a clock where I can control when I update its time, because lots of things might depend on that clock. and I don't want them all to get different times. I want them all to have the same time. So if I control when the clock ticks, basically this update function, think of it as like, when I tell the clock, okay, you can tick forward in time now, it's going to do that, and then everything that depends on that time will get the same value off of it. So this frame clock is really just a way to remember the current time value. So it's a signal, so I can call it like a function. Every time I call it, it's going to give me the current time that it remembered. And then whenever I want to tick the time forward, I just call this update function. And so because this is a signal, I can feed it into my sine wave. Like I can pass it into this time value. And so my time is a signal source. It expects either a fixed value or a signal. I can pass in this frame clock as a signal to that now. And that's exactly what I do in the main code for this. So look at how kind of cool and interesting this is. I've got my clock that I'm creating as a frame clock object, which is a frame clock signal. And now I'm creating my sine waves again. But now I'm telling them, hey, your time is based on this signal, this clock signal here. And that clock signal will change in the main loop. But my sine wave doesn't have to know or care, and my main loop doesn't have to know or care about, telling my sine wave to explicitly update its time. I've kind of captured that dependency in the configuration right here, where my sine wave has time based on the frame clock signal, and then it's also got some other parameters here that I'm changing. But my sine waves know that, so that now in my main loop here, it's even simpler. I update my clock, I tell my clock, okay, I'm at the start of a new frame, tick forward. And now I get my red value by just looking at my red wave and asking it, okay, transform your source signal into a value that falls within 0 and 255. And my red wave knows that its source signal is this sine wave. And my sine wave knows when it needs to get its current time, it should look at the frame clock signal. So it's going to bubble all the way back up to the frame clock and ask it, what is the current time? Which it stored after I did that clock update, after I told the clock to tick forward. So this is pretty cool. Just these 3 lines of code are driving this animation effectively, and it's really just these 6 lines of code right here that they're encapsulating all of the logic of this animation. How I define my signals. I have a clock signal. I have 2 sine waves that are driven off of that clock signal. And then they can have different frequencies. And again, I can change these frequency values. Like if I want to speed up my green so it's like really fast, I can do that. And then my main loop is just saying, okay, pump all of these objects, tick your clock forward, get your current red signal value, get your current green signal value, and then turn those into NeoPixel colors and push them out to your pixels here. And again, you can also look at how these values change. So I increased my green frequency, so my green changes really quickly, whereas my red value is still changing really slowly right here. So this is pretty cool, and this is getting even closer to I'm not thinking of my animation as how do I drive this loop and compute my current moment in time, and how do I go from my previous moment to my next moment and increase my glow or decrease my glow. I'm not thinking of it like that. I'm thinking it as signals. And I'm thinking it as I've talked so long that I've worn out the battery on that light over there. But anyways, we'll try to wrap it up on the next one more example left. Anyways, but again, I'm breaking this down into a signal problem now, so that I'm just composing signals in different ways. And so now it's even easier for me to add that blue signal. So, let's add a blue wave, and I'm going to make a sine wave. It needs to know its time. I've already got my clock, so I'm going to tell it, here's your clock signal. I don't have to use the clock signal. I could fix it so it's a fixed value if I wanted. I can give it whatever frequency I want. So, let's say my frequency equals 0.75, for example. We won't change the phase or anything on here, but I could if I wanted. I could do something really crazy, like set my phase equal to my clock value. I'll save this. It's going to make really weird random values, but I'll just show you, like, this works. This is perfectly valid. And then I can just ask, what is my blue wave value? And discrete transform that into the 0 to 255 range that I expect. And then when I construct my color, just make sure to use that blue component inside of there. I can save that. And so now I'm doing some really funky things. You're seeing the colors are going in different kind of crazy ways. You can see, and here's my blue value. But this is cool because my blue value now has a frequency that's fixed. The clock value is my clock, or my time is my is driven off the clock signal, but my phase is also driven off the clock signal. And that's kind of funky and kind of cool. Intuitively, this doesn't mean much because my clock is just always increasing, whereas my phase should be a value in radians. And so this is it's kind of like a meaningless value. You know, I'd want to transform this value basically to something more interesting potentially if I wanted to do that. But it's showing the power of this. Like, you know, I could make another type of signal. I could make a square wave signal that maybe I drive my phase based on a square wave so that, you know, my phase goes from a high value to a low value. And that's also, that changes how a sine wave goes in and out of phase in different ways. So again, you'll be able to get these really cool organic effects by combining signals. You know, I'm not thinking of how to do the code for this. I'm just thinking of what signals do I pull off the shelf? What knobs do I tweak on them? How do I wire them together? And how do I get output color like this? So this is kind of cool. I'm getting closer to that ideal of, you know, a fully configurable color synthesizer with this. So, okay, so let's go on to the final example here. This one is a little bit more advanced, but we'll see if I can kind of run through this one. Maybe we won't go through it in complete detail. So the last example here, this one is, I just took this idea to the next logical conclusion, because if I have a sine wave that I can drive off of any signal, like my time can be one signal, my amplitude can be driven by a signal, my frequency can be driven by a signal, what are other signal sources? And a really cool thing is, on this board, I have an analog to digital converter. I could hook up a potentiometer, a physical knob, like I have right here, a little breadboard potentiometer, so that when I twist this knob, I could make it so that it changes the frequency. I could hook this knob up so that this physical thing changes the frequency of this animation. And that's pretty cool. Like, that's, you know, you can imagine I could have a whole row of like little potentiometers that are all just generating different signals because, you know, the output of this potentiometer is just a change in resistance, which I can feed into the analog to digital converter. It can read that as a change in voltage. Voltage is a signal that changes over time. My sine wave is built to control itself off of signals, so I can just plug this potentiometer signal into my sine wave function however I want. If I want to modulate the frequency with it, if I want to modulate the amplitude, the phase, whatever, I can do that using these high-level primitives, which is really cool. So in this example, the signal source and the sine wave function are all pretty much exactly the same. And the frame clock is the same. I've added a new signal in here. I've added an ADC signal, an analog to digital converter signal. Now this one's really advanced. I don't think I have time to go through this because when you're dealing with analog to digital converters, you want to deal with, they're noisy. They don't give you always a good static kind of value. Like, you read it at one moment in time and then you read it immediately again. You might get a slightly different value just because the analog voltages fluctuate a little bit. So I do some things like I take multiple readings and I average them out, and then I also keep a running average, which is kind of like a low pass filter. Basically, I'm just smoothing out my analog to digital converter values in here. But it's nice that I can encapsulate that all into this analog to digital converter signal class. And there are some small differences right here that are noted between CircuitPython and MicroPython, so you might need to change how you read your analog to digital converter here, depending on what you're doing. But anyways, so I've created a new signal that reads from my analog to digital converter. So let's hook this potentiometer up and feed it in my analog to digital converter. So potentiometer, it has 3 pins. So if I hold this up, you'll notice there are 3 pins on this potentiometer. This is a nice breadboard compatible one. The way that this works is the 2 outer pins are connected to 2 ends of the potentiometer. The middle pin is connected to the wiper. And it's a variable resistor. So as I turn the knob, it just changes the position of that wiper, which just changes what resistance it sees. So you can set this up as a voltage divider effectively is how I do this. So I'm going to plug this into the breadboard, and the way that I wire this up, I want my maximum analog to digital converter voltage, my reference voltage, which on this feather is 3.3 volts. So I'm going to grab the 3.3 volt output of my feather, and I'm going to feed that into one end. So it's the far right pin on my potentiometer. Actually, I'm going to move it down so I can rotate it a little more easily. And it doesn't matter which end, it just has to be one of the ends. And then the opposite end, the far left end, or the far left pin, I'm gonna plug that into the ground value, oops, right there. So I'm gonna plug that into ground. So there we go. And with it plugged in the ground now, so the middle value is the last value, and I will plug that into one of my analog to digital converter channels. So if I plug this into analog channel 0, A0, so now my potentiometer is plugged into that, and if I turn my potentiometer, that's going to change the resistance, and then because I'm feeding in my maximum analog to digital converter voltage on one end and then ground on the other end, the voltage value on the output is going to change as that resistance changes proportionally. So just as I turn this knob, my voltage is going to go from 3.3 all the way down to 0, and then all the way back up to 3.3 again, depending on how I turn the knob here. And I describe how to hook this up in the example I mentioned in the comments up above here, how you want to hook up your potentiometer. But okay, so I've hooked up my potentiometer to that analog to digital input. And then I also created another signal here. I created a transformed signal because the problem is now I can get the value of my analog to digital converter. It's going to give me a value for this chip. It's a 12-bit analog to digital converter, so I get a 12-bit value. But if I want to modulate the frequency of a sine wave, I want to change within a much smaller range of values. I don't want to change within the full 12-bit 0 to 4096 range. I want to go from like 0.1 to 0.5. So I just thought about it as, you know, on my signal, I have that, these transform functions. So I can make a new signal that's just based on the output of another signal, but transforms it in some way and then returns it as its output. So that's what this transformed signal does. It's basically a way to take one signal and transform it, you know, change what range its values fall into and out of, and generate a new signal based on that. So I can take my ADC signal that has its known range of values and then create a transform signal that uses that ADC signal as its input and then outputs values that fall within a range that's better to modulate the frequency of my sine waves with. So that's what my transform signal class does right here. It needs to take in a source signal that it will remember, and then it needs to know what is the range of output values that you want me to output, because its source signal needs to be a signal that also has a range that's fixed. And then you can also tell it if it's a discrete signal or a non-discrete signal, and it will remember that. It just remembers which signal transform function to call, you know, basically whether it should call the transform function or the discrete transform function, because, you know, these are just those transform functions that are on the signal class that we saw before. So the transform signal just remembers which one it needs to call. And then whenever something asks the transform signal for its current value, it will just go back and ask its source signal for its current value and transform it into the range that it remembered. So it's going to give me a new signal that falls within a different range. And so it's easy for me to plug that into any of my other values here. So now here's the main loop for this. I'm going to save this and let's see what happens. So it's going between that red and blue animation cycle here, but let's see what happens if I change my potentiometer knob and I just cranked it up. So this is kind of cool. Notice it's glowing faster. And now if I crank this all the way down to a lower value, and you get these kind of little random things as it goes through some of the random values. Now it's a lot slower. You can see it's changing. It's going to red, but it's much slower. And so this potentiometer, this physical knob, is changing the frequency of this animation. And if I put it into like a halfway value right here, you know, now it's getting kind of halfway in between this range of frequencies. And so it's a little bit faster here. And this is where it gets really cool. All of this logic is encapsulated right here with like these 20 lines, if that, and there's really only maybe like 10 lines here just because I've broken it up across a bunch of things to make it more readable. All of this logic is just combining signals. So again, I have my clock signal, but now I have this frequency signal that I'm creating. And this frequency signal is a transformed signal that's fed by that ADC signal that's fed off of my analog to digital converter pin that I'm setting here. So here I'm creating that ADC signal. So that's, this class we looked at right here. So I've got my analog, I pulled off the shelf of my modular NeoPixel synthesizer, the ADC signal, and it's going to give me values that fall within a range of like 0 to 4095 or whatever. But that's not the range of frequencies I want. I want my frequencies to fall within the range of like 0.1 to 0.5. Before we were just manually setting these frequency values, like in the previous example code, I was setting the frequencies right here to values that were within like 0.1 and 0.5 or whatever. But now I'm telling my frequency, I'm going to make a frequency signal that's based on my analog to digital converter signal, but converts it into a range that falls within nicer frequency ranges for my animation effects. So now my frequencies will range from 0.1 at the low end. So when I tweak my knob all the way down to its lowest extreme like that, now it has a frequency value of 0.1. And if I look at the output of this, it's actually showing me here's my frequency value, here's my red, green, and blue color value. So you can see my frequency is 0.12. It's pretty darn close to that 0.1 minimum. I'm never going to get exactly down to that minimum just because the resistance to the potentiometer, there's small differences in it. But let's see, if I crank this all the way back up to the maximum value here, like that, then hopefully it should change. Oh, I might have just tweaked the code. Or I think my NeoPixel, there we go. I accidentally, the ground connection's not making a good connection. You can see I turned the knob all the way up to its maximum extreme value. My frequency is now 0.4999. Like that's basically 0.5, its maximum value. The animation changes a lot faster. And again, that's because it's seen that my analog to digital converter is at its maximum. So it's giving me a frequency value from this transformed signal that's at the maximum value I told it, like 0.5. So that, as I change my knob to like a halfway value, notice that frequency value changes halfway between 0.1 and 0.5. And then that changes my animation. Now it's animating at a slightly different frequency for that. So that's really cool, I think. And then I slightly changed things here so that, I took out the concept of having to have my main loop know to call that discrete transform function, because really I can just tell my main loop, here's your signal, trust that I've generated it in such a way that it will fall within the range of NeoPixels. And it can trust that because I can create a transformed signal and I can make this a discrete signal, an integer signal that goes within the range of 0 to 255. So just like I was using the transform signal to translate my analog to digital converter values into nicer, smaller frequency ranges, I can transform my sine wave signals into my NeoPixel range. So this is effectively a NeoPixel color component signal now, my red wave, that I can pass directly into my NeoPixel. And that's what my main loop does. I just make a color tuple that grabs my red wave, my green wave value at the current moment in time. And then to make my red wave, I make a transform signal that's driven off of a sine wave signal, that has a clock that's driven off of my clock signal that I set before, that has a frequency that's driven off of my frequency signal. So this is really cool. This is where it's getting that magic knowledge of when my frequency signal changes, my sine wave signals change. And I love how explicit and clear this code is, where you can really see those relationships. You can see, well, how does my red sine wave frequency change? Oh, it's driven off of this frequency signal right here. I don't have to drive it off that frequency signal. If I want to always fix my red frequency to 0.5, or let's set it to 0.25, that's perfectly valid too. Because remember, the way I constructed this, I can set either a static value or a signal, and it's going to do the right thing. So if I save the code here, now when I change the potentiometer knob, it's only going to change the green frequency. So if we look at the code here, look at the red column. It's always going to keep changing at this slow rate, but then watch the green column. So I'm going to set it all the way up to its maximum value. So you can see my frequency is 0.5. It's really fast. And so now my green column is changing pretty quickly, whereas my red column is still changing pretty slowly for this. And then if I turn my knob all the way down to, now my green frequency is actually even slower than my red frequency now. And it's cool. I mean, you can visually see this on the pixels. I get like that nice yellow effect because my red and green are intersecting at the same time. And you can see the green pixel is, it's a much slower sine wave compared to the red pixel, all based on just changing that little knob, which is hooked up to the analog to digital converter. So that's really cool. And I think something really kind of novel that I want to build on this, because again, this is a NeoPixel color synthesizer. This is the Moog synthesizer. Although, hey, I guess Moog was named after, I think Robert Moog was the guy who created it. So this is the Decola synthesizer. It doesn't run off the tongue as well, I guess, unfortunately. So, but I'm calling this the Decola NeoPixel color synthesizer, where I've built a NeoPixel color synthesizer right here. I can tweak this knob, it changes the frequency. I mean, look at that, that's kind of cool. And it's changing how the animation changes. But there's also code that drives this, and I can reconfigure my signals by just tweaking the code, and I can translate things like, if I want to make my frequency fall within like a 0.5 to how about 1.5 range, so now my frequencies are going to be really fast, I can do that too. So let's save this. And so now it's going to be like kind of a pretty spastic light show, but it's doing different things. I can slow it down a little bit like that, and you'll get kind of weird intersections of all these different sine waves and things. So, okay, so that's it. I'm going to wrap this up. I don't want this to go too much longer. Like I said, there's 6 examples. I'll put this code up as a gist on GitHub. And this is the start. I think I'm going to do at least one more video, maybe a third video on this, because I want to keep fleshing out this idea of animating NeoPixels based on plugging signals together, so that you get really cool effects and dynamic things, like hooking up to sensors, because an analog digital converter is one type of sensor, but hey, imagine a board like Circuit Playground. We've got accelerometers. Those are signals. As you tilt this, that's a signal that changes. There's a microphone on here. That's a signal that changes based on the sound pressure. There's a light sensor on here. That's a signal on here. There's all kinds of different signals. Even a button. That's a signal. That's an on-off. That's a square wave. I could feed that into something and control its behavior based on that. So that's really cool. And that's where I want to get to eventually, or with these experimentations, is turning these animations into combining signals and giving a bunch of interesting signal primitives like analog digital converter, potentiometer, accelerometer, whatever, sine wave, square wave, sawtooth wave, giving different filters that can change those signals, so that now when you want to do an animation, you just pull these different signals off the shelf, set their knobs how you want them, wire them together. That's basically what this code is right here. This is just that wiring code. And let it run. Now your main loop is just asking your signals, what is your current value? And because you've chained all your signals together in a certain way, they know how to talk to each other. They know how to convert their values into the ranges that they expect. Your code becomes very simple and really cool, because if I wanted to write this exact animation in the style as the very first example that I showed right here with just the raw code, it would be pretty crazy. I mean, I could do it. You're going to see a mess of sine wave function calls, and this would be code that I would write once and I would have no idea what it does anymore. And when I wanted to go change it later, I'd have to like remember what state of mind I was in, hope that I was like perfectly sober when I wrote this code, that I can remember it. Whereas, if I just take the effort to abstract away these things into higher level concepts of signals, I can plug them together. It's like Lego bricks, effectively. So I'm plugging together the Lego bricks of signals to build these cool things. So, okay, so that's it. I'm going to wrap up this stream. I don't think there are any questions, so we'll jump back to the main headshot view. Like I said, this one went a little bit longer. Maybe I showed more examples than I should have in this, but I wanted to really build this interesting case for where I want to go with some of these animations, because I want to make it easier to animate things in interesting and organic ways, so that you don't have to be a math expert to do it. You can just take cool signals and combine them and experiment and have fun. That's kind of the real kind of end goal for this, is giving you the toolbox to go and play with things, so that you can build fun stuff. And you might not know exactly how all the math behind it works, but you can take a potentiometer signal and a sine wave signal and feed them in certain ways to get cool effects. So, okay, this is Tony from Adafruit. Thanks a lot for watching. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos there. Check out twitch.tv/Adafruit. You can see me streaming these things live. I usually stream on Fridays, usually in the evenings. I'll stream this stuff. If you like this stuff, click the like or the comment or the subscribe button. Let us know that this is interesting content, and we'll keep doing it. So like I said, there's at least another video, maybe 2 more videos on this NeoPixel color synthesizer with CircuitPython and MicroPython. So thanks a lot for watching. I'll see you later.